This Prezi presents an overview of the TPACK framework specifically within the context of science education. You can navigate the Prezi by using your right and left arrow keys. What is TPACK? TPACK is a conceptual framework of a body of knowledge from which teachers draw upon to influence their practice. The framework consists of individual components, but is also concerned with transactional relationships among these components. TPACK is a relatively new framework, as it was suggested just over 6 years ago. However, it's rooted in a more long-standing model that's been around for over 2 decades. In order to better understand TPACK within the context of science education, it will be helpful to examine some historical events which led to its conception. The TPACK framework is founded on Schulman's model of pedagogical content knowledge, presented in 1986. Schulman explains that pedagogical knowledge includes knowledge of learner characteristics, strategies, and methods for teaching, and content knowledge is knowledge of the subject matter. Pedagogical content knowledge, he explains, is the knowledge base that practitioners use in order to teach their content. During this time, approximately 25% of high schools were using PCs for college and career guidance. K-8 schools were buying mostly Apple II and Macintosh computers, and high schools were buying DOS-based clones. Microsoft Windows had just been released in 1985, the year before. Computers were rarely used for instruction, but they were used for drill and practice at the elementary and word processing in secondary schools. In 1989, the Association for the Advancement of Sciences Project 2061 published Science for All Americans. This defined science literacy and identified standards for students in science, mathematics, and technology. In terms of technology, the TI Explorer, the first instructional graphing calculator, was developed with teachers 2 years prior, and 1989 marked the first release of Microsoft PowerPoint. 1990 marked the advent of multimedia PCs that included dedicated graphics and sound cards. These provided opportunities for educational videos, games, and simulations with animation and sound. Whiteboards replaced chalkboards, and although interactive smartboards were available the following year, it took nearly a decade for these to be widely adopted in classroom settings. In 1991, Tim Berners-Lee proposed what would eventually become the World Wide Web. The National Research Council published the National Science Education Standards in 1995. These provided guidelines for elementary and secondary schools to help students achieve scientific literacy. They promoted inquiry-based learning for students at all grade levels. Distance education was on the rise, nearly doubling in 2 years, and 78% of all public 4-year higher ed institutions were offering distance education opportunities. In 1998, the International Society for Technology and Education, ISTE, published the National Educational Technology Standards. Increased internet penetration and advancements in multimedia provided opportunities to use technology for student-centered, constructivist learning. AOL released their Instant Messenger, or AIM software, in 1997, and in a Menlo Park, California garage, in 1998, Google was founded. It was in 2002 that the No Child Left Behind Act was signed into law. This mandated high-stakes student testing and emphasized accountability of schools for student achievement. It also outlined penalties for schools that did not make adequate yearly progress. Friendster became the first social network on the World Wide Web. And the World Wide Web became a social place. In 2003, MySpace was released and quickly generated more users than Friendster. 2004 marked the first Web 2.0 conference, where the term was coined, referencing a more participatory, collaborative World Wide Web. Facebook was launched that same year, but did not overtake MySpace until 2008. And by 2006, individuals could share their every thought in 140 characters or less via Twitter. It was also in 2006 that new media literacies were introduced in a white paper titled Confronting the Challenges of Participatory Culture, Media Education for the 21st Century. The paper reflected on Web 2.0 culture and examined the type of participatory practices that youth were engaged in. It drew up a provisionary list of the skills that these practices demonstrate. These new media literacies were intended to represent the core cultural competencies and social skills required in a Web 2.0 world. It was also in 2006 that Mishra and Kohler introduced the TPCK model. In their publication, Technological Pedagogical Content Knowledge, a Framework for Teacher Knowledge, Mishra and Kohler outlined the model that they then termed TPCK. It was in 2007, at a meeting of the National Technology Leadership Institute, that the A was added for Technological, Pedagogical, and Content Knowledge, creating the acronym TPACK. TPACK is a multifaceted framework consisting of various components in the teacher knowledge base. We'll now examine the three main components of the TPACK model: technological knowledge, pedagogical knowledge, and content knowledge. Technological knowledge encompasses the knowledge and skills required to effectively learn, master, and utilize various technologies for information processing, communication, and problem solving. It encompasses knowledge about non-digital and digital technologies across various platforms and includes hardware and software. Pedagogical knowledge comprises a general conception of how students learn. This includes knowledge of theory such as cognitive, developmental, and behavioral learning theories, knowledge of assessment, motivational theory, and knowledge of strategies such as group discussion and inquiry. Content knowledge is the knowledge of subject matter. This is subject-specific. For example, science content may include an understanding of DNA, molecular structure, chemistry, astronomy, biology, and forces. Content knowledge refers solely to knowledge of subject matter. It does not include strategies or methods for conveying that knowledge to others. Let's take a look at a specific example from each component. Twitter is a social media application that allows users to tweet or send messages that are 140 characters or less. The use of technological knowledge is required to navigate the application. Concept mapping allows individuals to define various constructs and visually represent relationships between them. A teacher may elect to use concept mapping as a constructivist approach to meaning making. A knowledge of electricity and understanding of electrical current falls under the content area for science. Subject matter experts understand the principles involved in the generation and flow of electricity. While each of these examples provide a clear illustration of the knowledge component they represent, and each of these components is a necessary piece of the teacher's knowledge base, we can see that when we rely on each component individually, we are not likely to get optimal results. The random selection of concept mapping as a pedagogical strategy, electricity as a content focus, and Twitter as an opportunity for technology integration does not yield a thoughtfully designed or effective learning experience. And so we consider these components not in isolation, but as a complex framework for practitioner knowledge. This multifaceted model of teacher knowledge is actually fairly complex, as each component intersects and interacts with one another. We've already discussed technological knowledge, which includes both analog and digital technologies. pedagogical knowledge, which includes knowledge of learner characteristics, developmental and learning theories, and strategies and methods for instruction, and content knowledge, which addresses the specific subject matter of a field. But let's consider the way each of these components might interact with one another. Technological content knowledge is one possibility. This component considers only technology and subject matter. It does not include any aspect of teaching or learning. An example of technological content knowledge within the field of science is the understanding that microscopes are a specific technology utilized very frequently in biology. Another component of TPACK is pedagogical content knowledge. This consists of methods and strategies of teaching content, but does not consider technology. For example, a pedagogically sound approach to teaching the scientific method would be inquiry. The final component of TPACK is technological pedagogical knowledge. This includes the ability to align appropriate technologies with pedagogical strategies, but is not necessarily content specific. An example of this would be a teacher selecting a Web 2.0 application to allow students to create concept maps. This combination of media and method might be appropriate across various subject matter. It is when practitioners draw from each of these components that they exploit TPACK to its fullest potential. For example, an audio editing application might be used in a guided inquiry approach to teaching sound waves. A teacher draws on TPACK to inform this lesson with an understanding that sound waves are something that are best taught with visual examples. Guided inquiry is a particularly appropriate method for science content, and with the aid of an audio editing application, students can record sounds, manipulate them visually, hypothesize, test, and make inferences to explain their findings. Technological pedagogical content knowledge provides a model to understand the complexities of the teacher knowledge base. TPACK is a necessity for the effective integration of technology in science education.